Hello, my dear dreamers, and welcome back to my channel, where we soothe your mind and wander the cosmos, all from the comfort of your own rest. Before we begin our journey tonight, I have a small request. If the stories we explore here help you unwind and drift away, please consider supporting our community by subscribing to the channel and liking this video. It truly helps us grow and bring more peaceful adventures to you. Now, I am endlessly curious about where in the world you are listening from and what quiet hour has drawn you here tonight. So, as we travel together, please feel comfortable leaving a comment below telling me your name, where you are, and the time you're watching this. It's always wonderful to picture all of us scattered across the globe, looking up at the same stars and sharing a moment of peace. Now, get comfortable, close your eyes, and let your imagination float away with me. Tonight, we are traveling far, far beyond the edges of our solar system to a place where the universe performs one of its most dazzling magic tricks. We are going to uncover the secret of eternal diamond rain on distant worlds where entire mountains of glittering gems fall from the sky and stars themselves transform into diamonds larger than our own Earth. This is a story of cosmic alchemy, of how the simple element of life, carbon, becomes the universe's greatest treasure. So relax your breathing and let your mind drift on the solar winds as we explore the diamond extravaganza of the cosmos. My dear curious friends, welcome to my channel. Imagine the most precious, the most sought-after gemstone on Earth, a diamond. We dig deep mines, we move mountains, all to find just a few carats of these brilliant stones. Now let your mind travel far, far away from our world, to a planet so magnificent it's called the jewel of our solar system, Saturn. With its stunning, graceful rings, it already looks like a masterpiece. But I'm about to let you in on a secret hidden deep within its swirling golden clouds, a secret that makes all the treasures of our world seem almost ordinary. Because on Saturn, it is constantly, perpetually raining diamonds. Yes, you heard that right. Diamonds. Not water, not sleet, but genuine glittering diamonds. This isn't science fiction. It's a breathtaking scientific theory based on the intense chemistry and physics of that distant gas giant. To understand how this magical, almost alchemical process works, we have to take a journey from the top of Saturn's atmosphere all the way down to its mysterious core. So, fasten your seatbelts and let's dive into the stormy skies of this incredible planet. Our story begins with something very familiar. A thunderstorm. But a Saturn storm is nothing like the ones we experience here. Imagine, if you will, the most ferocious thunderstorm you've ever experienced here on Earth. The kind that makes your windows rattle and lights up the entire sky with brilliant forks of lightning. Now take that image and multiply it by 1,000, no, million, and you might begin to approach the sheer, awe-inspiring power of a Saturnian storm. What we consider catastrophic weather on our planet is merely a gentle drizzle compared to the atmospheric beasts that roam the skies of this gas giant. These aren't just storms, they are continent-swallowing, planet-encircling monsters that can rage not for hours or days, but for months on end, with some observed by scientists lasting for well over 5 months without interruption. That's right. While we on Earth might endure a week of rainy weather, on Saturn, a single thunderstorm can dominate the atmosphere for nearly half an Earth year, with some particularly tenacious tempests even lasting longer, becoming the longest continuously recorded storms observed on the ringed planet. When we talk about lightning in these storms, We're not referring to the spectacular but relatively modest bolts we see during our terrestrial thunderstorms. The lightning strikes on Saturn are of such monumental power that they defy easy comprehension. Scientists recording these events have discovered that Saturn's lightning bolts can be up to 10,000 times more powerful than anything ever witnessed on our home planet. Just let that number sink in for a moment. A single one of these colossal energy discharges, these Saturn electrostatic discharges, or SEDs as researchers call them, releases more raw power than all the lightning strikes in a massive terrestrial hurricane combined. This isn't just a flash in the sky. It's a fundamental reshaping of the very atmosphere, a cosmic sledgehammer that literally forges new matter from the gases that swirl through Saturn's skies. The radio signals these lightning events produce are so intense that they can be detected by spacecraft millions of miles away, and during the most active periods of a storm, flashes can occur at the almost unbelievable rate of more than 10 times per second, creating a nearly continuous light show of unimaginable proportions. Now, to understand the true magic of what happens next, we need to look at what Saturn's air is actually made of. If you could somehow take a deep breath of Saturn's atmosphere, which, I must quickly add, would be immediately fatal for many, many reasons, you'd find it's composed mostly of hydrogen and helium, about 75% hydrogen and 25% helium, with traces of other substances. But hidden within this mixture is that small but crucial ingredient I mentioned earlier, methane gas. Now, methane might not sound particularly exciting. It's the same natural gas we might use for cooking here on Earth. But in the context of Saturn's atmosphere, it's the literal seed of something extraordinary. A methane molecule is beautifully simple in its structure, almost like a microscopic tetrahedron or a three-legged stool. One central carbon atom happily bonded to 4 hydrogen atoms floating through the alien skies. It's this simple arrangement that holds the key to one of the most spectacular natural phenomena in our solar system. When those tremendous lightning strikes I described earlier crack their way through Saturn's atmosphere, they deliver a massive jolt of energy that's powerful enough to shatter those meticulously arranged methane molecules apart. This process is something scientists call dissociation. The incredible energy of the lightning bolt literally tears the hydrogen atoms away from their carbon heart. The lighter hydrogen atoms, now separated from their carbon partners, simply float away, blending back into the vast hydrogen-helium soup of Saturn's atmosphere. But what's left behind, after this violent divorce at the molecular level, are countless tiny particles of pure carbon. We know these particles by a much more familiar name here on Earth, soot. That's right, the same fundamental substance that makes up the black residue from a candle flame or a forest fire. It's almost humorous to think that the first step in creating something as beautiful and valuable as a diamond begins with something as common and unglamorous as soot. But that's the wonderful irony of the cosmic chemistry happening in Saturn's skies. Think about that for a moment, and let the sheer wonder of it really sink into your imagination. A lightning bolt on Saturn doesn't just create a brilliant flash and a rumble of thunder that would deafen any human listener, if there were anyone there to hear it. It literally creates the building blocks of precious gems from thin air, or rather, from thick atmospheric gas. It performs the ultimate alchemy, turning invisible gas into solid particles that hold the potential for greatness. It's as if nature has its own cosmic factory, where the raw materials are gases and the machinery is pure planetary energy. This process of turning methane into soot through lightning is the foundational step, the genesis moment in the life cycle of an extraterrestrial diamond. Without these spectacularly powerful storms, without these unimaginably energetic lightning bolts, the entire miraculous chain of events that follows would never begin. The diamonds of Saturn are born from tempests of almost unimaginable violence, a beautiful paradox in a planet known for its serene, jewel-like appearance in our telescopes. Now, these newly born specks of carbon soot are most definitely not diamonds yet. Not even close. If we were to follow their journey with some sort of magical microscopic camera, they would look like nothing more than black, fluffy, incredibly fine powder, similar to the soot you might find in a chimney or from an extinguished candle wick. They are just the raw material, the unformed clay, if you will, the cosmic ingredients waiting to be baked into something spectacular. And as they are born in the upper atmosphere, riding the fierce winds of Saturn, they begin a long, long fall, a descent of epic proportions that makes the journey of a raindrop on Earth seem trivial by comparison. Gravity, that fundamental force that rules the universe, pulls them down, drawing them inexorably deeper and deeper into Saturn's immense atmosphere. Saturn's gravity is about 10.4 meters per second squared, compared to Earth's 9.8, so the pull is slightly stronger, but it's the incredible depth of the atmosphere that makes this journey so extraordinary. As these carbon particles fall, the environment around them changes in ways that are almost impossible to visualize from our earthbound perspective. The pressure increases dramatically. Imagine the weight of not just a few miles of atmosphere above you, but thousands of miles of hydrogen and helium pressing down from all sides. We're talking about pressures that build from something similar to Earth's surface pressure to thousands, then millions, and eventually billions of times greater than what we experience. Meanwhile, the temperature begins to rise as our soot particles descend into the planetary interior. While the upper cloud tops of Saturn are incredibly cold, around 130 degrees Celsius to 250 degrees Celsius, things get progressively hotter as you go deeper. This isn't a gentle warming. It's a dramatic increase into realms of heat that would vaporize any known material from Earth in an instant. The soot particles, now beginning their epic transformation, are traveling into a world of extremes that pushes the very definition of matter itself. After falling for about 1,000 miles through this increasingly hostile environment, something remarkable begins to happen to our traveling specks of carbon. The pressure becomes so immense, so fantastically powerful, that it starts to squeeze and compact these flakes of soot in a way that fundamentally changes their internal structure. They are no longer a loose, fluffy black powder floating in the atmospheric currents. Under this incredible squeeze, something akin to a cosmic forging process begins. The carbon atoms, which were previously arranged in a fairly random, disorganized pattern, typical of soot, are now forced to rearrange themselves into a new, more organized form. The immense pressure literally pushes the atoms into neat, stacked layers, creating a new structure that we Earthlings are very familiar with. Graphite. Yes, the very same substance you find in the center of your everyday pencil. When you write on a piece of paper, you're actually just leaving thin, delicate layers of graphite on the page. It's a humble substance, but in the context of Saturn's atmosphere, it represents a crucial second act in our cosmic drama. So, let's pause and appreciate the journey so far. The carbon has gone from being a gas, methane floating freely in the upper atmosphere, to a solid powder, soot, created by lightning, and now to the slippery, layered sheets of graphite. It's already undergone two incredible transformations, each one moving it closer to its ultimate destiny. But the most spectacular metamorphosis is still to come. The graphite chunks, now more structured and dense than the original soot, continue their relentless fall, pulled ever downward by Saturn's powerful gravity. Saturn, being a gas giant, doesn't have a solid surface to land on. So this journey can continue for depths that are almost incomprehensible in terrestrial terms. We're now traveling to regions about 6,000 kilometers down from the cloud tops, descending into one of the most extreme environments in our entire solar system. Here, the pressure is almost unimaginable, millions of times greater than the air pressure we feel at Earth's surface. To put this in perspective, the pressure at the deepest part of Earth's ocean, the Mariana Trench, is about 1,000 times atmospheric pressure. The pressure our carbon particles are experiencing now is thousands of times greater even than that. It is a hellish, crushing environment where the very rules of chemistry and physics as we know them begin to bend and twist. The temperature has also risen to thousands of degrees, creating conditions that are both incredibly hot and under immense pressure simultaneously. And it is here, under these fantastic, extreme conditions, that the real magic truly happens. The same intense force that has been compressing the carbon throughout its journey now pushes the atoms in the graphite so close together that they undergo one final, magnificent rearrangement. They lock into an incredibly tight, incredibly strong crystal structure that is renowned throughout the universe for its perfection and durability. The structure of diamond. Can you picture it? In the deep, dark skies of Saturn, far below the visible cloud tops where sunlight never penetrates, chunks of solid diamond, some scientists estimate as large as a centimeter across, which are essentially perfect, uncut gemstones, are hailing down through the hydrogen-helium atmosphere. These aren't microscopic specks. These are genuine diamonds of a size that would be considered precious here on Earth. Researchers have even playfully suggested that some of the largest could be big enough to adorn a ring. Of course, uncut, and of a size that a Hollywood star like the late Elizabeth Taylor would have been proud to wear. It's a breathtaking image, a perpetual shower of glittering gems falling through the eternal darkness of Saturn's interior, a spectacle of cosmic extravagance that has been ongoing for billions of years. The scale of this diamond production is equally staggering. Scientists estimate that this natural process creates about 1,000 tons of diamonds every single year on Saturn. To put that almost unimaginable quantity in perspective, even the largest diamond mines on Earth seem modest by comparison. The Aikal mine in Russia, one of the largest natural diamond mines on our planet, holds about 175.56 million carats of proven and probable diamonds. Compared to Saturn's endless glittering showers, even Earth's richest mines pale in comparison. This isn't just an occasional phenomenon. It's a constant, planetary scale process that churns out precious gems on an industrial scale, all through the natural workings of chemistry and physics. But the story doesn't end there. The diamonds, being much denser than the surrounding liquid and gas, continue their relentless descent. Imagine those newly formed diamonds, each one a perfect uncut gemstone, some as large as a centimeter across, genuine celestial hailstones of pure carbon. Having already traveled thousands of miles, you might think their journey is nearly over. But in the vast, deep interior of a gas giant like Saturn, the journey is only just beginning. These diamonds are now embarking on the most epic leg of their voyage, a plunge of another 30,000 kilometers downward toward the planet's mysterious core. To truly grasp the scale of this fall, picture it like this. It's a distance equal to about 2.5 times the entire diameter of our planet Earth. That's an immense, dark, and increasingly hostile space to traverse, and as they fall, the environment around them becomes more and more extreme, pushing past the boundaries of what we can easily comprehend. The pressure, already millions of times greater than what we experience on Earth's surface, continues to build to almost inconceivable levels. Simultaneously, the temperature soars to staggering heights, reaching levels that are hotter than the surface of our own sun. We're now entering a hellish forge at the center of the planet. It is here, under these fantastically brutal conditions, that the diamond, the hardest natural substance known to us, meets its match. The very same incredible pressure that helped create it now, combined with the blistering heat, becomes its undoing. The mighty diamond, which seemed so permanent and indestructible, cannot withstand this hellish environment. The incredibly strong bonds holding the carbon atoms in their rigid, beautiful crystal lattice begin to vibrate, strain, and finally they break. The solid diamond can no longer maintain its structure. It begins to melt, undergoing its final dramatic transformation. The diamonds, which spent so long forming and falling as solid stones, now dissolve. They don't burn or vaporize in the way we're familiar with. Instead, they turn into a liquid sea of carbon. Can you picture that? A vast, hidden ocean, not of water, but of liquid diamond, sloshing around the core of Saturn. It's a concept so alien, so magnificent, it's difficult to fully grasp. Some scientists have playfully and poetically suggested that these liquefied gems could pool together, forming literal seas or rivers of liquid carbon, perhaps even with solid diamond bergs, giant mountain-sized chunks of solid diamond floating in them like cosmic icebergs. This isn't just a beautiful spectacle. It might be a key part of the planet's very engine. This raining material, as it sinks and melts, can create currents within the planet's interior. On planets like Saturn and Neptune, the movements of such conductive fluids are fundamental in generating their powerful magnetic fields. So, this dazzling diamond rain isn't just for show. It could be a crucial piece of the puzzle in understanding the inner workings and very heart of the gas giant itself. Now, you might be wondering, how on Earth, or rather, how off Earth, do we know all this? It's a brilliant question, and it gets to the very heart of how science works when it can't just go somewhere and look. We can't exactly pack a suitcase, book a flight to Saturn, and lower a diamond-catching net into its atmosphere. The pressures and temperatures we've been talking about would utterly destroy any spacecraft we could possibly build. Think of the Cassini probe, a magnificent piece of human engineering that spent years studying Saturn. When its mission was over, scientists deliberately plunged it into the planet's atmosphere, where it was crushed, melted, and vaporized long before it could even get close to the depths where diamond rain forms. It's the environment so brutal, it makes the inside of a volcano look as cozy as a living room. So if we can't go there, how can we be so confident? The evidence comes from a beautiful combination of clever chemistry, fundamental physics, and some truly spectacular, almost science fiction-like experiments conducted right here in the safety of our own laboratories. It's a bit like a cosmic detective story, where the clues are the laws of physics themselves, and the crime scene is the entire solar system. Scientists are like the ultimate puzzle solvers. They start with what they do know about Saturn, things we can measure from afar. We know its overall size and mass, which tells us about its density and gravity. We can study its atmosphere with telescopes and spectrometers, which tell us it's made mostly of hydrogen and helium with a dash of methane. We can measure its powerful magnetic field. All of these are pieces of the puzzle. Then, using the fundamental laws of physics and chemistry, the same laws that work in your kitchen or your car, scientists can build a mathematical model of what must be happening inside the planet to create the conditions we observe from the outside. It's like knowing the ingredients of a cake and the temperature of the oven, and then being able to predict that the center will be soft and gooey, even if you can't stick a toothpick in it from 1,000,000 miles away. But a mathematical model is just a theory. To test it, you need an experiment. And this is where things get really clever. To recreate the insane pressures inside these planets, scientists use some of the most ingenious tools ever invented. One of the most important is called a diamond anvil cell. Now, don't let the fancy name fool you. The concept is beautifully simple, even if the execution is incredibly complex. Imagine a miniature vise, the kind a watchmaker might use, but instead of metal jaws, it has two tiny, perfectly cut diamonds facing each other, point to point. Why diamonds? Because, as we know, they are the hardest natural substance we have. You can squeeze them together with immense force, and they won't flatten or break. They'll just push back. Now, scientists place a vanishingly small sample of material, let's say a speck of methane or a bit of graphite, the pencil lead we talked about earlier, in between these two diamond points. Then they turn a screw or use hydraulic pressure to squeeze the diamonds together with incredible force. Because the tips are so incredibly small, all that force is concentrated into an area tinier than a pinprick, creating pressures that can reach millions of times the atmospheric pressure on Earth. They can then heat the sample with a laser, raising the temperature to thousands of degrees, all while watching what happens to the material through a microscope or by probing it with X-rays. It's like creating a tiny, tiny piece of Saturn's interior right here on Earth and watching the chemical reactions unfold in real time. They have literally watched carbon compounds turn into diamond dust under these conditions, proving that the first step of our cosmic story is not just possible, but probable. But to get to the even more extreme conditions, like those found at the very core of Saturn where the diamonds themselves melt, scientists need even more firepower. This is where the big guns, or rather the big lasers, come in. More recently, researchers have used gigantic laser facilities, like the famed National Ignition Facility in the United States. This place is like something out of a superhero movie. Its goal is to research nuclear fusion, but it's also perfect for planetary science. At its heart are 192 of the world's most powerful lasers, all focused with perfect precision on a single tiny target that's smaller than a peppercorn. This target contains a speck of the material they want to study. When they fire all these lasers simultaneously, they deliver a mind-boggling pulse of energy to that tiny spot in a burst that lasts only a few billionths of a second. This doesn't just squeeze the material, it creates a powerful shockwave that compresses and heats it to extremes that even a diamond anvil cell can't reach, momentarily creating pressures and temperatures that match or even exceed those at the very core of Saturn. In these experiments, they have compressed samples of diamond itself, watching as it transitions from a solid crystal into a hot, dense liquid soup of carbon, directly confirming the final act of our story, the creation of those liquid diamond oceans. It's a breathtaking feat of engineering that lets us hold a piece of a planet's heart in a lab for a fraction of a second. And the science is always evolving, always giving us new and surprising insights. For instance, in 2024, an international team of scientists used a different kind of incredible machine, an X-ray laser called the European XFEL, to look at this process in even more detail. What they discovered was fascinating. Diamonds can actually form from carbon compounds at even lower pressures and temperatures than we previously assumed. This might seem like a small, technical detail, but it has huge implications for the universe. This means that diamond rain could begin forming higher up in the atmospheres of the ice giants, Uranus and Neptune. And it gets even bigger than that. If diamond rain can happen more easily, it means it could even be possible on a whole different class of planets outside our solar system. The smaller, mini-Neptune exoplanets that we're discovering around other stars. Suddenly, diamond rain isn't just a quirky feature of our own gas giants. It might be a common weather pattern throughout the galaxy. These experiments, where they shock common hydrocarbons like polystyrene, basically styrofoam, with lasers and watch diamonds form in nanoseconds, are truly our windows into these distant, mysterious worlds. They confirm that the chemistry we believe is happening isn't just a wild guess. It's a robust, testable, and repeatable process that the universe seems to follow. It's also fascinating to compare Saturn to its planetary siblings because the recipe for diamond rain changes slightly from planet to planet, leading to different outcomes. Jupiter, for instance, Saturn's bigger brother, is also thought to experience diamond rain. It has a similar gas giant composition and its own set of terrifying planet-sized storms like the Great Red Spot. So, the basic process should be the same. Lightning turns methane into soot, pressure turns soot into graphite, and deeper pressure turns graphite into diamond. However, the internal structure of Jupiter might be different enough that the diamonds there might not grow as large, and they likely melt into liquid carbon much closer to the core, just like on Saturn. However, the conditions on the ice giants, Uranus and Neptune, are a different story altogether. They are called ice giants, not because they're cold, though they are, but because they are thought to have a much higher proportion of what scientists call ices. Not just water ice, but frozen compounds like methane, ammonia, and others. This means there's a lot more carbon to go around in their atmospheres. There, a similar process is believed to create diamond rain, but with a dramatically different ending. Because the cores of Uranus and Neptune are thought to be much cooler than the infernal cores of Saturn and Jupiter, the environment at the bottom of their atmospheres might not be hot enough to melt the diamonds. So, the diamonds there may never melt. Imagine that. Instead of falling into a liquid sea, the diamond hail would just keep accumulating. They could sink down and form a thick layer around the core, a glittering diamond blanket thousands of miles deep. Some scientists have even theorized that the immense pressure could compress this accumulation into a gigantic solid diamond crust, a literal diamond core, a treasure of almost unimaginable scale that remains solid forever. There's even a fun, though still highly speculative theory that under the incredible pressures at the very heart of Neptune, carbon could be squeezed into a single, monstrous diamond the size of a person. It's a wonderful thought, isn't it? That deep within the cold blue depths of Neptune, there might be a diamond as big as you are, a permanent gem at the center of a world. This comparison shows us that while the universe follows the same physical rules everywhere, it can mix the ingredients in different ways to create an astonishing variety of wonders, from the liquid diamond seas of Saturn to the potential solid diamond hearts of its distant icy cousins. And the diamond extravaganza doesn't stop within our solar system. Out in the cosmos, there are stars and planets that make Saturn's diamond rain seem almost modest. Venturing beyond our solar system to where the diamond extravaganza reaches truly astronomical proportions. We've marveled at the diamond rain falling through the skies of Saturn, a spectacle of almost unimaginable grandeur. But out in the wider cosmos, nature performs even more breathtaking feats of alchemy, creating diamonds on a scale that makes Saturn's glittering hail seem almost modest. The universe, it turns, has a fabulous sparkling side, and it's time for us to explore it. So, let's begin with the star of the show. Quite literally, a star that is a jewel. A white dwarf star named Lucy, and what a perfect introduction she is. To understand Lucy, we first need to understand what a white dwarf is. Imagine a star like our own sun, a brilliant, steady ball of light and heat. For billions of years, it fuses hydrogen into helium in its core, holding itself up against the immense force of its own gravity. But nothing lasts forever. Eventually, such a star will run out of its nuclear fuel. It will swell into a red giant, its outer layers drifting away into space, and what remains will be the star's hot, incredibly dense core exposed to the cosmos. This core is a white dwarf. It's a stellar ember, a cosmic cinder. Now picture this. A typical white dwarf packs a mass comparable to our entire sun into a volume no bigger than the Earth. That means a single teaspoon of white dwarf material would weigh as much as an elephant here on Earth. It's an object of almost unimaginable density, held up not by the fires of nuclear fusion, but by a quantum mechanical effect called electron degeneracy pressure. A fundamental force that simply says the subatomic electrons inside cannot be squeezed any closer together. And what is this incredibly dense core made of? For stars like the one that became Lucy, it's primarily carbon and oxygen, the ashes of the star's long extinguished nuclear furnace. Now, this is where the real magic begins. For decades, scientists have theorized that as a white dwarf cools down over billions of years, the incredible pressure inside would cause its carbon core to solidify, to crystallize. Think of water freezing into ice, but instead of turning into a block of ice, this star is slowly turning into a block of crystal, a crystal of carbon, which is by definition a diamond. The entire core of the star undergoes a phase change, with its atoms locking into a perfect, rigid lattice, just like the diamonds we know on Earth, but on a scale so vast it defies all comparison. This brings us to the star you mentioned, BPM 37093, affectionately nicknamed Lucy by astronomers, after the classic Beatles song, Lucy in the Sky with Diamonds. Located about 50 light-years away in the constellation Centaurus, Lucy is a variable white dwarf, meaning it pulsates, its brightness flickering rhythmically. And for astronomers, those pulsations are a gift. They act like seismic waves, allowing scientists to peer into the star's interior, much like geologists use earthquakes to understand Earth's inner structure. This technique, called asteroseismology, allowed researchers to make an astonishing calculation. They determined that approximately 90% of Lucy's mass has crystallized into a gigantic diamond structure. Just let that sink in. 90% of a stellar corpse, an object with a mass about 1.1 times that of our sun, has turned into diamond. Now, how big is this diamond? Lucy is about 4,000 kilometers across. To put that in perspective, that's roughly the distance from New York to Los Angeles and back again. The entire continental United States would fit comfortably inside this single gem. Its weight is a number so staggeringly large, it loses all meaning, approximately 10 billion trillion carats. Our entire planet's yearly diamond production, all the jewels in all the royal collections, every diamond ever mined. They are all utterly insignificant, invisible specks of dust next to the magnificent cosmic grandeur of Lucy. She is a testament to the fact that the universe doesn't just create small, precious stones. It can forge entire stars into the most precious gem imaginable. And while Lucy is the most famous, she is not necessarily alone. Scientists have identified other white dwarfs, like HD 190412c, that are also in the process of crystallizing, suggesting that diamond stars might be a common, if spectacular, end for stars like our own sun billions of years from now. It's a truly poetic end to a star's life. After a long and brilliant life of shining in the sky, it transforms into the ultimate cosmic treasure, a diamond in the sky for eternity. But the universe's diamond-making prowess doesn't stop with stellar remnants. It also forges entire planets from this sparkling material. You mentioned two fascinating examples, 55 Cancri E and PSR J17719-1438b. These are exoplanets, worlds orbiting stars other than our sun, and their stories are just as compelling, though in very different ways. Let's start with 55 Cancri E, a planet that captured the public's imagination when it was proposed to be a super-Earth made largely of diamond. This planet orbits a star called 55 Cancri A, which is part of a binary star system about 41 light-years away. A super-Earth simply means a planet with a mass larger than Earth's, but substantially less than that of ice giants like Uranus and Neptune. It doesn't necessarily mean the planet is Earth-like or habitable. In the case of 55 Cancri E, it's anything but habitable. It's an inferno, orbiting so close to its star that a full year on this planet lasts only about 18 hours, and its surface temperatures are hot enough to melt most metals. The initial hypothesis that it was a carbon-rich diamond world was thrilling. The idea was that the planet and its star formed from a cloud of material that was exceptionally rich in carbon. Under the intense heat and pressure within the planet, that carbon could have crystallized into a thick layer of diamond, potentially making up a large part of the planet's interior and even its structure. It was a world envisioned as a gigantic, blazing hot jewel floating in space. However, as you correctly noted, later studies have made this dazzling picture less certain. More refined measurements of the host star's composition suggest it may not have as much carbon relative to oxygen as initially thought. If there's more oxygen, the planet's composition would likely be dominated by silicate rocks, more similar to Earth's crust, rather than carbon and diamond. So, while 55 Cancri E remains an intensely fascinating and extreme world, the current scientific consensus is shifting away from it being a pure diamond planet. It's a wonderful reminder of how our understanding of the cosmos evolves with new data, and that sometimes the most alluring theories must be refined as we learn more. This brings us to the second exoplanet, PSR J1719-1438b, which presents an even more bizarre and exotic story. This isn't a planet that formed in a protoplanetary disk of dust and gas like Earth or Jupiter. Instead, this object is the incredibly dense, crystalline remnant of a once mighty star, and its history is one of cosmic cannibalism. It orbits a special kind of stellar corpse called a millisecond pulsar. A pulsar is a rapidly spinning neutron star, the superdense core left behind after a massive star goes supernova. It beams radiation like a cosmic lighthouse, and we detect it as a rapidly repeating pulse of radio waves. The story scientists have pieced together is that this pulsar was once part of a binary star system. Its companion was a white dwarf, much like Lucy. Over time, the pulsar's immense gravity began to strip material away from the white dwarf companion, siphoning it off. This process transferred angular momentum, causing the pulsar to spin faster and faster, hence the millisecond in its name, while simultaneously devouring its companion. The pulsar essentially acted as a cosmic vampire, stripping away more than 99.9% of the white dwarf's mass. What was left of the poor white dwarf was no longer massive enough to remain a star. It had been whittled down to a planet-sized object. But this object inherited the extreme density of its white dwarf origins. The immense pressure from its own gravity, even at this reduced size, is thought to have crushed the carbon material into a crystalline state. The result is an object so dense that its atomic structure has collapsed into the tight, rigid lattice of diamond. So, PSR J1719 1438b is not a planet in the traditional sense. It is the ghost of a star, compressed and transformed into a planet-sized diamond by its voracious partner. It's a celestial phantom, a glittering relic of a stellar tragedy. When we step back and look at this incredible cosmic picture, from the diamond rain on Saturn and Neptune, to the diamond heart of the white dwarf Lucy, to the potential diamond worlds like PSR J1719 1438b, a profound pattern emerges. The element carbon, which is the essential chemical backbone of life here on Earth, the very element that makes up our bodies and our world, also has this other fabulous, sparkling side. Across the universe, under the right conditions of extreme pressure and temperature, carbon atoms are drawn together, forging bonds of incredible strength, arranging themselves into the beautiful, crystalline structure we call diamond. It happens in the atmospheres of giant planets, in the cores of dying stars, and in the remnants of stellar encounters. This demonstrates a fundamental and beautiful unity in the laws of physics and chemistry that govern our entire universe. The same rules that form a tiny diamond deep within the Earth are also at work on a scale spanning thousands of kilometers in the heart of a star. It seems that the universe has a deep appreciation for sparkle, creating these magnificent diamonds not for anyone to wear or own, but simply because the physics is elegant and the conditions are right. It is a hidden, sparkling side of creation, a testament to the fact that the cosmos is not only vast and powerful, but also capable of producing wonders of breathtaking beauty, all from the simple, humble carbon atom. And so, as our cosmic journey comes to a gentle close, we're left with a truly dazzling thought: that the same element that gives us life, the carbon in our very beings, is also out there, sparkling in the eternal darkness, forming diamonds on a scale we can barely imagine. From the raining gems of Saturn to the heart of a diamond star, the universe is far more wonderful and creative than we could ever dream. I hope this story of cosmic treasures has calmed your mind and carried your imagination to a place of wonder. If it helped you unwind and escape for a little while, I'd be so grateful if you'd let us know by liking this video. And if you haven't yet, please subscribe to Hafee Sleep and ring the bell. It's the easiest way to ensure our next peaceful adventure finds you right when you need it. I'd love to continue this journey with you. As you drift off, please share a little of your world with ours in the comments below. Tell me, where are you listening from, and what time is it for you right now? It's a beautiful thing to picture our community of dreamers, connected from every corner of the globe, all finding a moment of peace under the same vast, starry sky. The universe is full of secrets, and we'll explore them all together. For now, let the image of those distant, glittering worlds soothe you. Breathe deeply, let go, and drift into a peaceful, star-filled sleep. Good night, my dear dreamers.